Hello and welcome. In today's video, we are going to talk about the new Wi-Fi technologies and Wi-Fi 7. So stay with me, your presenter Osama Al-Khatib. So in our agenda today, we're going through several topics about the Wi-Fi evolution, key technologies, Wi-Fi 7, and top 5 gotcha for site surveys and interference. And I will leave you with some common RF terms for your reference. So to start with, we're talking today about the Wi-Fi evolution. And as you have noticed, I mentioned Wi-Fi 4 and the upcoming, or let's say the next standards that came after Wi-Fi 4. Because in my opinion, the most advancements and the most improvements, most of these improvements happened in Wi-Fi 4 and back in 2009. Although Wi-Fi itself started back in 1997. So why Wi-Fi 4 was important? Well, because it was the first standard to have the dual band. So it supports 2.4 and 5 gigahertz. It has a larger QAM table. And of course, they introduced the multi-input, multi-output or MIMO. So this was a building stone for the next standards in terms of Wi-Fi, Wave 2, where they have a larger QAM table. They introduced new security measures like WPA2 for authentication, and also they have the multi-user MIMO, and also more special streams. And next they had the Wi-Fi 6 and Wi-Fi 6E as of today. All right, so the main improvement was in having OFDMA compared to OFDM, and we're going to discuss that in the upcoming slides. Also, we had the support for WPA3 security, a better security than the WPA2 for authentication and encryption. Also, we had downlink and uplink multi-user MIMO. And then we had the new technology, which utilizes the 6 gigahertz, which is Wi-Fi 6 and Wi-Fi 7. So although Wi-Fi 7 is not yet released by most of the vendors, but in my opinion, most of the vendors are going to release products about Wi-Fi 7 in upcoming year. So although we are happy about the 6 gigahertz and all the benefits and how it will make our life easier in terms of planning, designing, and also user experience, but not all of the countries have adopted this range, the full band, which is 1.2 gigahertz range, wide range of 1.2 gigahertz. Some of the countries have adopted half of that, right? So this is, as of now, maybe countries will move to full adoption. We hope so. But as of today, these are the countries that have on the right that have moved to full band of 6 gigahertz. So what are the key technologies and advancements between Wi-Fi 6 and Wi-Fi 6E over Wi-Fi 5? Well, we have a lot. We have the downlink, uplink, or FDMA. We have downlink and uplink multi-user MIMO, a larger QAM table. It means we can carry more data. Very simple. Also, we have more spatial streams, extended range, special density, and of course we have the target wake time or TWT. We have WPA3, PSS coloring, tri-band support because now we have 3 bits, of course. So among these improvements, also we don't need to forget about WPA3 because WPA3 is a major enhancement in security where WPA3 requires protected management frames to be enabled. Right, so the PMFs enhances the Wi-Fi security and network protection from malicious attacks, such as spoofing by providing data confidentiality and replay protection of management frames. So these are the highlights about WPA3. It's the next generation from WFA, It simplifies enhanced file security, robust authentication, greater cryptographic. This allows legacy protocols like TCAP, requires project management frames, and also we have the transition support with WPA2. And this comes handy if you have a mix of endpoints that still doesn't support WPA2. So you don't have to create two SSIDs. You can create one SSID, and the authentication will be WPA3 transition. So if the endpoint doesn't support or the SDA doesn't support WPA2, WPA3, so it will fall back to WPA2 pre-shared key. Also, we have the SAE handshake, which means that we have a more robust way of having forward secrecy, so we don't rely on the password as a major component in the encryption. We have also different ways for encryption. We can talk about this in next videos. Easier security for IoT, and a major improvement is if you have today WPA2 or if you have open networks, right? Without WPA3, it means your traffic over the medium or the wireless medium is not encrypted. Although you can rely on application layer like HTTPS to encrypt your traffic, but the traffic itself can be sniffed and can be seen by anyone nearby who has the required equipment. We have also optional a minimum 192-bit security for sensitive environments, and also WPA3 is not suspected anymore to crack replay attack. So for the PMF, for the protected management frames, it means that we don't have eavesdropping. So we have several frames or management frames that will be protected. Among these management frames are de-association or de-associate. We have de-authenticate action frames like block ACK request responses, collective service admission controls, radio management, spectral management, fast PSS transition, channel switch announcements. But although we have all of these encrypted, we still have some, let's say, entry frames not encrypted, like beacons, prop requests, which makes sense because we cannot have these encrypted because it didn't yet establish the connection with the access point. Also, among these, authentication, association, request and response, and so on. So, when we compare now Wi-Fi 6 versus Wi-Fi 6E, what are the technical differences? So, obviously, Wi-Fi 6E has the 6 gigahertz, and we are utilizing AFC, automated frequency coordination, which means for outdoor, of course, access points, which means that there is a proactive mechanism to avoid interference. While in 5 gigahertz, we have the DFS, or the dynamic frequency selection. So this method monitor the channels, the Unit-2 channels in 5 gigahertz band, and if there is any interference, or let's say non-Wi-Fi traffic, they kick in the DFS procedure, and the access point will move to a different channel, non-Unit-2 channel, and it will also tell the STAs to move to that channel, right? And in Wi-Fi 6E, WPA3 and OWE is mandatory, and there is no other methods. So it means that your endpoint has to support WPA3 if the endpoint requires to connect to 6 gigahertz. And of course, we have the channel widths, recommend channel widths with Wi-Fi 6 of 40 and 20 and 40. This is recommended, although you can go to 80, but it's not recommended in the enterprise environments. Why? Because we have so many channels now, almost more than the double of what we have in the 5 gigahertz. We have more chance of flexibility in bonding channels. So typical use 40/80. RTS CTS protection is required in Wi-Fi 6 because it is backward compatible with older standards. So we have to have this. while we don't have to support, because all of the inputs that supports 6 GHz has to, it's actually new endpoints or new software. So we have discovery, and the Wi-Fi 6 can be done on all channels via propping or via beacons, while the discovery uh, for the 6 gigahertz is done different methods, but we have the out of band, which can be this can be done by propping the X point on 2.45 gigahertz, or have something we call PCS, which is preferred scanning, or PSC, sorry, preferred scanning channels. So efficiency gains, right? So in the Wi-Fi 6 or Wi-Fi 5, and the X point contends with the legacy clients for the medium in traditional way. So there is no advantage of the use of trigger frames for the uplink channel access. While in the Wi-Fi 6E, we have something called MU-EDCA, which is multi-user enhanced distributed channel access. It's a QoS, quality of service enhancement, to give priority to the access point channel access over the STA or the endpoints. So then now the X point controls and schedules the uplink data transmission from the STA. And of course, we have the spatial reuse, which is the goal of this spatial reuse is to ignore transmissions from OBSS and therefore be able to transmit at the same time. So the 802.11ax amendment defines two independent spatial reuse modes. One is called OPSS PD based spatial reuse, and the other is called SRP based spatial reuse. We are not going to discuss these two modes in this video. Maybe I will discuss these advanced topics in upcoming videos. Now about the difference between OFDM, OFDMA, although they look very similar to each other in the first fourth letter, but they are different. So OFDM stands for orthogonal frequency division multiplexing, and the OFDMA, which is orthogonal frequency division multi-access. So the difference is, assuming that we don't have multi-user MIMO, just for simplicity and conversion, right? So if you have a channel of 20 megahertz wide, you can transmit on this channel and to communicate with one endpoint, right? It means that one can communicate with this channel. Right, so at this time I'm communicating with the STA1, and this time I'm communicating with ST2 and ST3 and so on. Why with the OFDMA? Actually, what we are doing here is we are creating sub-channels, and the right term for that is resource units. So we have these resource units, up to 9 resource units that can be distributed on stations based on the application need. So on this time, I'm communicating with 2 stations instead of 1, and I can communicate with 3 and can communicate with 4, and dynamically adjust to the requirements. So just to highlight, because I hear a lot of guys not able to distinguish the difference between multi-user and MIMO and OFDMA. And although multi-user MIMO is supported in Wi-Fi 5, right? It was introduced in Wi-Fi 5, while the OFDMA is introduced in Wi-Fi 6. So the main difference is the OFDMA itself is dividing the channel into smaller channels. It means we have now smaller channel, smaller bandwidth. So the main idea of having this kind of dividing channel is to have more clients, and the application or use case, let's say with the OFDMA, is the OT IoT. So it suits low bandwidth applications, reduce latency because now we have less competition on the channel, and it improves performance and efficiency. While in multi-user MIMO, it's an advanced mathematical and utilizing of multipath to achieve this kind of multipath. So the same channel, the same width of the channel, 20 megahertz, let's say, can be used to communicate with multiple users and some of the access points can reach 8 users, right, depending on the vendor and the hardware. But we can communicate with multi-users in downlink or the uplink. So it means now we have more bandwidth, so boost capacity, high speed connectivity, and actually it suits the high bandwidth applications. So one of the advancements when we compare Wi-Fi 6 and Wi-Fi 6E with the Wi-Fi 5 and previous standards like Wi-Fi 4 is that we have a larger QAM table of 1024. So it means that we have more capacity to carry data at the same time. So it means 10 bits per sample, right? So it's a huge advancements, and when we have a larger QAM table, it means we can carry data at the same more data at the same time. So what is QAM? QAM is actually a highly developed modulation scheme in which data is transmitted over radio frequencies. For wireless communication, QAM is the signal in which two carriers, which are shifted in phase by 90 degrees, are modulated. And the resulting output consists of amplitude and phase variations. So we have phase and we have amplitude variations. When we verify the phase and we verify the amplitude, we have a new symbol, right? So more advancements is the target wake time, or the TWT, which means that this TWT enables devices to determine when and how frequently they will wake up to send or receive data. So essentially, this allows the 802.11ax APs to increase device sleep time, and they said it's up to 5 years. So you can see how flexible, although it's not a valued case, but it's very flexible that it can allow a device to sleep for 5 years and significantly improve the battery life. And of course, this is good news for OT and IoT uh, devices, because with a limited battery time or battery lifetime, you can increase that lifetime. So the TWT enables wireless access points also and devices to negotiate and define specific times to access the medium. And this will help optimize spectral efficiency by reducing contention and overlap between users, or let's say devices, especially for OT and IoT. But actually, this is also linked to the endpoint. So if the endpoint decided to ignore that, it can do that, and it can uh, be omitted from the TWT. And also one of the enhancement is the BSS coloring, right? So BSS coloring, so it's a way to optimize the efficiency and reuse of spectrum in high density deployments, especially in my opinion, 2.4. So we use a technique that includes basic service set SS coloring, multi-codes, multi-bits that can be used and can be attached to the preamble. So this mechanism intelligently color codes, let's say, or marks shared frequencies and shared frequencies with number, or that is included within the physical layer. So again, it's included in the preamble. We have set of bits that can be shared between the access point and the associated users with that, so they can avoid the conditional interference. So in this example, for example, I can see that we have a user here and he's nearby. He's associated to AP1, but he's nearby AP2, and they are working both on the same channel. So with the old standard, without the BSS coloring, the user has to sense uh, the physical medium, the wireless physical medium, and of course has also a virtual uh, mechanism to sense the medium, but it has first to see if the medium is clear to send and then decide to send. But because AB is also communicating with different users and it's not aware of this user, right? So the user has to wait and the AB has to wait also for this. But with the BSS coloring, it means if the user see a communication that is not meant to be within his own cell, which means that the nearest AP who is associated with, it means this user can communicate and ignore the communication on the same channel if this communication is done via different cell. So the automated or automatic frequency coordination is a way again for access points, outdoor access points, to avoid proactively the interference. So how it works, so the access point checks in to the AFC provider. It reports its own coordinate, it requests a channel, a check with a list of channels already incumbent, and it makes sure that it doesn't interfere with the incumbent. And this happens once per day. So in US, this is OpenAFC, but the rest of the world, there are several regulatory that are looking to become an AFC provider, like Broadcom, Google, Wi-Fi Alliance. It's already used in cellular, and they are going to move it to Wi-Fi. Again, AFC is a proactive approach, while the DFS on 5 GHz is more of a reactive approach. So for the Wi-Fi 7, and we're going to communicate about Wi-Fi 7 in the next slides, but since we are talking about outdoor and indoor, there are specific unis in the Wi-Fi 7 that is meant to work in the outdoor, which is Wi-Fi Uni 5 and Uni 7. Okay, so for the access point, when it works in the outdoor, it's allowed to use standard power mode. It means the access point can reach up to 36 dBm, and the clients have to be lower by 6 dBm, so they are allowed to go to a maximum transmission power of 30 dBm. So how discovery is working, or typical discovery on the 2.4 and 5 GHz is working via passive mode, let's say passive way, which is listening for beacons, and the active way, which is sending props. All right. So when we send prop, we are sending on every channel in the 5 GHz or 2.4, and we are waiting for the access point to respond. Of course, this can be in certain vendors, certain software, this can be suppressed for security, but the access point has to respond if it's configured to do that. So how is the discovery working with 6 GHz? So as you can see here, the 6 GHz propping could be out of band. It means we can prop the access points on the 2.45 GHz and wait for the result. And the result should include also the 6 GHz SSIDs. And why this is happening, because we have too many channels. We have 59 channels, right? We need to send too many props if we need to do active propping on every channel. It will take time, and sometimes we will miss the access point. So the outband discovery method, it uses the RNR, reduced neighbor report. So the access point will report this information via RNR. And the station or the STA should not do that on the active propping on the 6 GHz cell itself. But there's also a different way, which is in-band now, active propping on PSC. So PSC stands for Preferred Scanning Channel. So we specify certain channels for scanning, so to respond for propping. So it's actually maybe client independent. So it means that not all clients may support it. PSC channels are only active in the 20 megahertz every fourth channel. So as you can see, this is the PSC channel. This is not PSC. So we scan or prop here, we prop here instead of propping the entire 59 channels. So maybe good news and bad news. So good news, actually for security, that WPA3 is the only method supported, of course, with a 6 gigahertz. It means we don't have open, unencrypted SSIDs. This will be replaced by OWE, Opportunity Sequence Encryption. So even with an open SSID without authentication, we can still have encryption. And no more pre-shared key. So we use the SAE, simultaneous authentication of equals. Also, we have the MFP, management frame protection, means that the management frames are encrypted. And it doesn't, it's not actually backward compatible with WPA2 and Open. So no transition mode on the 6 GHz, while it's available, of course, on the 5 GHz. So examples. So we have Enterprise WPA2, we have the Enterprise WPA3, we have a PSK personal pre-shared key, we have the SAE, and OpenGuest, we have the OWE. Of course, with the IoT, there's different methods. We can discuss that on different video. So a very important topic here is usually now we will start to hear about requirements of having Wi-Fi 6 and Wi-Fi 6E available, right? Replacing the old standards of Wi-Fi 5, Wi-Fi 4, and the question will come in by a lot of clients and colleagues is, can we do rip and replace for the access point and just replace it, just move the access point and put the new one? Well, the answer, it depends. It depends on the use case. So I will tell you the following. If we have an opportunity in hotel deployments, right, where typically we install access point in the ceiling in each room, right? So yes, we can do that because the hotel rooms are limited in space. So yes, we can do that. And home deployments, yes, may be acceptable, right? However, for the enterprise, planning is needed. So planning is needed. Site survey is needed. New heat maps are needed to verify that the 6 gigahertz, because it has a shorter wavelength, right, compared to 5 gigahertz and 2.4. So it means that the path loss is higher with the 6 gigahertz. So LPI, low power indoor. So in Wi-Fi 6E and 6 gigahertz, it comes with two modes. So low power indoor and the standard mode. So some mode is for the outdoor and the low power indoor is for the indoor installation. So the maximum transmission for the indoor access points is 30 dBm, and the endpoint itself, the LPI endpoint, has to be lower by 6 dBm. So the maximum ERP of the endpoint has to be 24, right? So excluding, of course, the Uni 5 and Uni 7. So number of channels, again, depending on the country, but in US and other countries, we have 59 on 24, 29 on 40, 13 on 80 megahertz, 7 on 160 megahertz channel bonding, and 3 potential 320 megahertz. While in Europe, we have almost half of that, and even less than half of that. So key enhancements. So I'm talking about the bands. Of course, now we have 3 bands in Wi-Fi 6E and Wi-Fi 6. And we have also the Wi-Fi 7. We have 3 bands. Although Wi-Fi 6 itself is not supported, 6 GHz is not supported in Wi-Fi 6, but just to know that it's only supported with Wi-Fi 6E. So general bandwidth, we have 40 maximum channel bonding, maximum of 160 channel bonding. Of course, we have the option of 80 plus 80. It depends on the vendor and the hardware, software. Here in Wi-Fi 6 or 6E, maximum 160, and in Wi-Fi 7, we will have 320 megahertz. QAM table. So we have 46 QAM of the M, 256 QAM of the M. Modulation for the Wi-Fi 6 or 6E is 1024 QAM of the MA. And of course, we have the 4K QAM of the MA with the Wi-Fi 7. So key features, also we'll discuss that in the upcoming slides. So as you can see, it was 4x4 MIMO. Now we have 8x8 downlink. And here we have uplink and downlink multi-user MIMO. WPA3 security compared to WPA2. Beamforming was there. And also we have here the BS coloring, target wake time. Here we have the multi-link operation MLO, and we have the multi-RU functioning. So max throughput is 40, theoretical max throughput in good conditions is 46.4 gigabit per second compared to 9.6. Huge, more than 4 times. So with the 6 gigahertz, we have more channels, more than actually 2 times the channels, and 1480 megahertz. So now 80 megahertz is a kind of practical way to be adopted in the new band. So Wi-Fi 7. Wi-Fi 7, in my opinion, is going to be the next improvement, and we are going to discuss that, the biggest improvement, since we have the Wi-Fi 4. Again, throughput rate, sometimes it depends actually, but let's say between 30 gigabit, and we have also the up to 46 gigabit. Of course, higher bandwidth mentioned earlier, more spatial streams, 16, right? And it's planned again to be in 2024. So higher modulation means more data per symbol, 12 compared to 10 in Wi-Fi 6. So Wi-Fi 7 will support advanced modulation scheme of what we call 4K QAM. It increases throughput and capacity, so transmission should be more linear in amplifying power. It requires higher SNR, and we are going to discuss that. So in terms of reality for the 4K QAM table, so in order to achieve this kind of 4 QAM and the high MCS or the modulation coding scheme, it means we have to maintain a high SNR, right? So assuming that in typical use case, we have a noise floor of minus 90 dBm, and if you tell me that you need to maintain a value of 41, let's say plus minus 41 dBm of SNR, it means that your RSSI has to be within the 49 or minus 49 dBm, right? It's higher, it's high value, especially if you have a large enterprise deployment to maintain this kind of value. But it comes with a cost, of course. So compared with 32 in the Wi-Fi 6 or 6E with the 1024 QAM, and of course compared with a lower QAM table, 256 QAM, which requires, let's say, plus minus 25 dBm. And usually we design our network with plus minus 25 difference from the noise floor for voice and real-time applications. Of course, resource units, and this is the idea of the MA, is that you have now resource units up to 9 resource units. We have 242 tones, and these tones are divided into, let's say, resource units. So we can have up to 13 resource, or let's say, tones within a resource unit. So multi-resource, small versus large. So we have the multi-resource units, so it can go down to 26 tone up to 996 tones. That's a huge advantage, and we're going to discuss how we can have this. So the Wi-Fi 7, or what we call it 802.11be, allows more granular use and management of the RUs. So the term multi-RU makes full use of every resource. So with the Wi-Fi 6 and Wi-Fi 6E, each user can only send or receive frames on an assigned resource unit, which significantly limits the flexibility of the spectrum resource scheduling. So how we solve this problem? So to resolve it, we enhance the spectral efficiencies by allowing multiple RUs to be assigned to a single user and can combine RUs for increased transmission efficiencies. So it's more flexible for usage. And of course, the flexible channel utilization is achieved on preamble functioning. This is the key. Preamble functioning allow this usage. So when we talked about the Wi-Fi 6, Wi-Fi 6E, when any part of a large high-speed channel is being used by another device, the entire channel is unavailable, and a difference channel must be selected. With the multi-RU functioning, right? So the Wi-Fi 7 devices will be able to use other parts of the same high-speed channel not in use to enable very large channels. So the key for the multi-RU is the channel or PML function. So before every when the channel is busy, meta bands couldn't be fully used. So it has to go through different channel. So another big enhancement actually in Wi-Fi 7 is the multi-link operation. So multi-link operation will allow the Wi-Fi 7 devices to deliver massive throughput gains. So we use the wider channel and multiple medium, so we can utilize multi radios. So let's discuss this in details. So the Wi-Fi 7 that uses multi-link operation is called MLD, okay, multi-link devices. So the multi-link devices can work in different ways: single radio operation and multi-radio multi-link operation. So the idea here, instead of using, let's say, 6 gigahertz for sending and transmitting, you can now use 2.4 or 5 gigahertz or the 3 radios to transmit and receive. So depending on the goal, we have the MLO method. So if you want higher throughput, we use the link aggregation. So we utilize the 3 links. If you need a lower latency, we use link steering. So depending on which radio or which band is better for my use case. Let's say I don't have a lot of contention on 5 gigahertz, while I have so many, say, contention on 6 gigahertz or 2.4, I will go with 5 gigahertz. And of course, the third goal is if we need to have increasing reliability, we need to have the link redundancy, which means that I can transmit duplicated data on both links and then use these data to recover any corrupted bits. So data aggregation, again, both data, we fragment the data and we send the data into the 2 radios. Redundancy, we duplicate the data and we can recover now the data with the duplicate sector, and we have link steering depending on the use case. Now, if 6 gigahertz is better, we go with 6 gigahertz. If 5 gigahertz is better, we can go with 5 gigahertz. How that works? So the multi-link operation and the MAC layers. So of course, there is something has to be done with the software and how we can have multi radios communicating at the same time is by introducing what we call virtual MAC layer. So we have introduced a new layer, which is the universal MAC, which is a link agnostic. So regardless of if it's 6 gigahertz or if it's 5 gigahertz, I have a unified MAC here, and down there we have very specific physical layer and link layer for the MAC layer for the specific physical band, right? How we do the discovery? So we have something called multi-link element, MLE. So similar to what we have mentioned in the multi-link, in which multi-link takes advantage of that feature to also gather which resources are available to support the multi-link. So using the MLD, the multi-link operation devices, to gather a list of MLE variables. Of course, we have different modes for the multi-link. So if we have multi-link single radio, MLSR, in this mode we have to transmit and receive over one link at one time. And we have the enhanced MLSR, EMSLR, can also listen to two links at the same time. So non-simultaneous transmit and receive multi-link multi-radio, and STR, MLMR, so can transmit and receive over two or more links simultaneously under certain conditions. Of course, we have it simultaneous transmit and receive multi-link multi-radio, STR, MLMR, can transmit and receive over two or more links simultaneously. Of course, this will be our target, but it depends, of course, on the conditions. And of course, we have the enhanced multi-link multi-radio, EMLMR, can also listen to multiple links at the same time and switch the transmission between them. So top 5 gadgets for site survey. So I would say a great network starts with a great design. So, and in other words, there is no great configuration that can fix bad design, right? So we have to be careful, have to spend our time in designing the Wi-Fi, and also use antennas similar to those planned for actual deployment. So if you are going to do a site survey, use the same antennas that are planning to use in the deployment for the site survey. So the site survey is a verification for your deployment. It's not a model. It's not a template that you can reuse multiple times, because every use case is different. Every environment is different. So a use case for warehouse is different than even factory, or different factories. They have different floors, different heights, different material. And so take the measurement of the RSSI on both sides of the walls. And never assume that the measurement on one side will give you all the data. And this has to also to do with the free path loss and the if you want to reflect the actual value of the attenuation happens by this material or this wall, is simply you need to go to the site, you need to have your access point on a stick, and you need to install this access point in the middle of the room, let's say, right? So you take the measure, let's say 2 meters or 5 meters away from the access point, and then you take another measurement after the wall, but this time take it like 10 meters from the access point itself. So you double the distance. By doubling the distance, you are also having a -6 loss of dBm from the signal strength. And by measuring this RSSI, you can subtract the two values between the RSSI that was taken on the 5 meters and 10 meters, and also remove 6 demand, and then you will also have the real attenuation value for that wall. So the last one is that you have to design and measure for latency in WLAN deployment. So it's also recommended to think that even if the deployment is not about voice and video, it's also good practice to design, because these are real time. It means if you design your network for real time, it can also be good for other use cases. And also you have to take into consideration the least capable, most important device at CMI. It means that you need to discuss with your customer about what is your most important devices, and get a list of these devices and check which device has a limitation in terms of capabilities on that radio. So for example, transmission power, radio standards, or let's say 802.11 standards supported, like if it only supports say N, or it supports 2.4. So you have to have your design to accommodate this device. Interference. Interference is more of an issue at the receiving antenna than the transmission antenna, because the signal there at the receiving side is much weaker at the receiving antenna, right? And the occlusion value refers to how well physical items interfere with the signal and are dependent on three things. The first thing is the proximity for the occlusion to the receiving antenna, the material of the occlusion, and of course the angle of the occlusion to the receiving antenna. And some occlusions are variable, seasonal, foliage, vehicles, large body of waters, and occlusion, or let's say attenuation, is not always bad. Actually, you need that in indoor deployments, right? If you want to maintain a high signal strength RSSI, receive signal strength, in the rooms, okay, you need to have something that can absorb the signal from the other areas, right? Because by not having appropriate attenuation, it means you will most likely have uh, co-channel interference between the access points. So interference occlusion values, typical values that are, let's say, recommended, but also you can verify that using using your own tools, right? So dry walls, we have 3 dBm, bookshelf 2 dBm, up to elevator shaft, which is typically measured at 30 dBm signal loss. So common RF terms, I will leave you with this slide. And that was my presentation. Thank you for watching.